Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. So today we will continue our lesson on our first chapter for this subject, which is the embedded system. So for the first chapter, what we will be learning is all about the introduction to embedded system. Right, so let's just proceed with the lesson. Okay, so for introductions, what is actually defined as embedded system? An embedded system is a computer system with a dedicated function within a larger mechanical or electrical system, often with real-time computing constraint. So basically what defined as embedded system is, it is actually the same as computer system, but it only serves a dedicated function within a larger system. Alright, for example, you have a mobile phone, right? In your mobile phone, there is an embedded system which will operate just to operate your mobile phone. So that is the dedicated function for your embedded system. But on the other hand, a general purpose computer is designed to be flexible and to meet a wide range of end user needs. Right? So for example, your own computer, your PC or your laptop, it is not an embedded system because it serves a very general functions. Right, for example, you can watch the video, you can simulate something, you can design by using by using SolidWorks and so on. You can do a lot of things inside your computer. So that is not the embedded system. So embedded system, it is actually computer-based system, but the function of embedded system is only to do or to serve some dedicated function only. Alright, so the example of the embedded system, as you can see here, there is a newer version of Raspberry Pi, which is the Raspberry Pi 5, and the other one is the NVIDIA Jetson Nano. So for Raspberry Pi, usually we do some mechanical things, we do some electrical, electronics and mechanical functions, okay? For example, you wanted to move your robot, or you wanted to move your auto gate, or you wanted to move something, okay, so you can use Raspberry Pi. So in the other hand, NVIDIA Jetson Nano, it is actually an embedded system which is used for deep learning, image processing and so on. So that is the dedicated functions which has been designed specifically for the embedded system itself. Alright, so that is the differences between embedded system and also the general purpose computer. Alright, so next is the embedded system applications. So as we have seen from the definition of embedded system, which is a computer-based system that serves a specific functions, alright? So for specific function, for example, here you can see mobile phone, cars, this is the radios, alright? Printers, phones, camera, and so on. Alright, so each devices has their own embedded systems, alright? So for the applications of embedded system is so wide. Alright, for example, in automotive, in government, in medical equipment, in consumer, in communication, and also in aerospace electronics. So every device has their own embedded system. Okay, so the embedded system, the function is to do or to execute what the devices have to do. Okay, so for example, for mobile phone, okay, the embedded system, it is used to make a call or take a picture. So those are the functions of embedded system. Right. So next is the embedded system features. So embedded system, inside the embedded system, there is often it is based on microcontrollers. Okay. So microcontrollers is actually a CPU with integrated memory or peripherals. Right. So for embedded system, the size of embedded system, it is actually a small size. The design has been optimized, and the cost of embedded system is low, right? Because they wanted to increase the reliability and the performance. And also for embedded system, it is usually mass produced. Okay, for example, for your mobile phone, the mobile phone is actually being mass produced. Lots of people, everyone has a mobile phone nowadays. Okay, so they need to mass produce the product, right? So physically in portable devices, stationary installations, machines, appliance, telecommunications, surveillance, medical, military, and etc. So this is the application of embedded system that we just see in the previous slide. right? So basically, inside the embedded system, they have microprocessor. Okay, so the microprocessor, for example here, the NVIDIA Tegra K1. So this is a microprocessor embedded system, which is used for deep learning. All right, and then this is the next one is the Apple A17 Pro chipset or microprocessor, which is used for the newest iPhone, which is iPhone 15 Pro Max or iPhone 15 Pro. All right, so it is used to execute the tasks of mobile phones. All right, and then this is the Raspberry Pi 5 chip, which is from the Broadcom, a microchip company. It is used to execute some operation, GPIO, general purpose input output operation, inside the Raspberry Pi. Right, so basically embedded system, it is often based on microcontrollers. Right, so NVIDIA Tegra, it is embedded into microcontrollers. The Apple A17 Pro is embedded inside the mobile phones, and the Broadcom chipset here, it is embedded inside the Raspberry Pi 5. Right, so what is actually a microprocessor? Okay, so a microprocessor is actually a digital chip which reads and executes a program stored in the memory. So its operation are controlled by the program. Okay, so basically microprocessor is a chipset which is included inside the microcontroller. So I'm sure that you already clear about this because you have learned microprocessor. You have learned this inside your micro P subject last semesters, right? So basically microprocessor is actually a chip. The function of the chip is just to read and execute a program. For example, if you code a program or if you execute a program, it will process the program by using microprocessor lah, right? And then what is a program? So the program is actually a sequence of binary coded machines instruction to be executed. Okay, so what actually inside the program is just like a binary coded machines, binary coded instructions, right? So for example, when you use a computer lah, for example, when you use a computer, right? And then you have a processor, for example, Intel Core i7. Okay, and then right now you are running Microsoft Word. Okay, so when you are typing inside Microsoft Word, so those typing or those processes are being processed by microprocessors. Okay, so the thing, for example, you write HELLO, hello. Okay, so you write hello and you see inside the interface in front of you on your monitor. But what the microprocessor receive is just like a sequence of binary coded machines. So a sequence of binary. Okay, they cannot read what you type. Okay, but they need to convert it into binary language. Alright, so that is a program. Okay, next is the memory. So the function of memory here, it is to store program and data. Okay, so for example, if you run, for example, Microsoft Word, okay, so the program that you are running, it needs to be saved into a memory. Okay, because in order for the microprocessor to execute the program, it needs to temporarily save the program into a memory. So it is easier lah for the microprocessor to call the function, to call the processes and so on. Right? And then you have input and output here. So input and output, the function of input and output is to provide interfaces between microchip and outside world. Okay? And it is usually used in general purpose digital computers. So basically for input, your keyboard, your mouse, so that is the input of your microprocessor. Okay? So the output from your microprocessor, you can see, which is from the monitor. Okay? So that is a microprocessor, right? Which is a digital chip that can read and execute a program which is stored in the memory. Okay? When you run a program, the program will be stored in the memory, and the microprocessor will call the function, get the input and output from the memory lah. Right? So that is the microprocessor. And it receives only binary code lah. Okay? Not like the HELLO. No, it's not that. Right? Okay, so next is a computer system. Okay, so this is actually a general computer system. It is not an embedded system. Right? So computer system architecture, they have microprocessor, they have memory, they have external peripherals and internal resources, and all of those are being controlled by using the microprocessors. Okay, and then they also have clock lah, which is the heartbeat of your computer. So if your clock or if the battery of your clock is malfunction, so your computer cannot function well. Okay, I think cannot function at all. Right? So this is the example of the motherboard of the Asus ROG Strix. So this is a computer motherboard. Alright, so inside the motherboard, okay, the CPU, alright, is installed here. Okay, so the CPU here, which is the microprocessor, will control all of the process, all of the program that is run inside your computer. Right, so for microprocessor-based systems, all right, has a differences lah between the microcontroller-based system. Okay, so in microprocessor-based system, the microprocessor chip is, we call it separated from the EPROM, from the BIA, address decoder, and so on. Okay, so it is being separated. So after this, which is the next slide, I will show you the micro controller based system. So this is the microprocessor, and this is the UART. UART is actually to translate data between the chip and the serial port lah. Okay, so this is the UART driver, which is used to simplify reading and writing to any of the UART peripherals. Okay, so this is, for example, RS-232. Okay, so it is used to convert from the information that you get from the microprocessor here to the peripherals. All right. So as you can see, this is ACIA. ACIA is actually a asynchronous communication interface adapter, right? So it is actually providing the communication data formatting, okay, such as the means of controlling other communication peripherals lah. So it is being connected to the UART driver, okay? So this is the PIA, is the peripheral interface adapter, which is actually a peripheral integrated circuit providing the parallel I/O interfacing lah for microprocessor system lah. So this is being connected to the micro P to manage the interfacing of your microprocessor. So this is the address decoder, which is basically to select lah the memory cells inside your memory devices, right? And then this is the EPROM. So EPROM is actually erasable programmable read memory. So it is actually used to store the memory, okay? And it doesn't lose any data when the power supply is being turned off. So it is a little bit different with the RAM, random access memory. So for random access memory, it is actually a part of computer main memory, okay, which is directly accessible by your microprocessor. But for the RAM, the data inside the RAM will be erased when you shut down the computer or shut down the board, right? So this is the microprocessor based system, which is the microprocessor is being separated from all of the other chip that is being used for processing. Right, so this is the data and address bus. Alright, so basically this is the CPU, which is the microprocessors. So the CPU will be interacted inside the memory. Okay, when you run a program, the program will be stored inside the memory. Okay, and the CPU will be interacted only with the memory. Okay, so it will execute the system based on the data of the system which is being stored inside the memory. Okay, so this is the CPU. They are connected by using the address bus, and the memory will give the data to the CPU by using the data bus. Alright, so inside the memory you have EPROM and you have RAM lah. Alright. Okay, so for the data and address bus, the smallest transferable data from memory to CPU and vice versa is 1 byte. Okay, basically the smallest data that you can transfer back and forth from the CPU and memory is only 1 byte. Okay, so each byte have a unique location or address. So this is the address, alright, so which is stored inside the memory. So each byte or each data have their own unique location or unique address. Okay, so that when you wanted to get the data, it will not being we call it conflict. You don't have any conflict with the other data, right? So each address are written in hexadecimals. So hexadecimals, okay, as you can see 0x000000 until 0xFFFFFF. So this is in hexadecimal. So address inside the memory is in hexadecimals. Right, so the range of addresses is accessible by the processor is the memory space. So the amount of address that you have inside the memory is depending on the size of the memory. So for example, if your memory is 4 GB, 8 GB, 16 GB, alright, 32 GB, so the number of address is being we call it depends on the number or the capacity of your memory. So that is the data and address bus. Alright, so next is the microcontroller. Okay, so previously I already mentioned it to you about the microprocessor, where the microprocessor is being separated from the RAM, from the memory, from the converter, and from the other peripherals, okay, from the other components that requires your CPU or your microprocessor to, we call it to operate. But for microcontroller, okay, so we call it incorporated everything, the microprocessor, the analog digital converter, the oscillator, the RAM, the program memory, inside only one chip. Okay, so that is the differences between micro C and also micro P, right? So a small computer on a single chip, which is containing on a chip resources, processor, memory, input and output. Alright, so this is actually typically embedded inside some devices that they control. And then a microcontroller is actually often small. It is actually really small and it is low cost. Alright, and it may not requires extra of chip resources to function. Okay, so it can function by itself, okay, by using the micro C chip. Right, so that is the differences between micro C and also micro P. Alright, so what is the advantage and disadvantage of micro C? So why does sometimes we can use micro C and sometimes we cannot use micro C? Okay, so the advantage of micro C is actually less chip required. Okay, so when we have using the micro C, we actually required less chip. Okay, because when we wanted to design a system which is a very small size, so we need to use a micro C because the size of the micro C is smaller compared to a micro P base, we call it base system. Okay, and then the other advantage of micro C is lower power requirement. Single chip power requirement are less than external components. So it means that when you use micro C, okay, the power required for your micro C is less than the power required for your external components. Okay, so it means that you can save some power from your micro C. Alright. Okay, but for disadvantage of your micro C is difficult or impossible to expand the internal memories and I/O. So you need to carefully choose it. So the main disadvantage of your micro C, it is less customizable. You cannot expand the memories, you cannot expand the capacity of your storage, okay? And it is hard for you to design a modular system by using micro C lah, because you cannot upgrade your system, okay? And in the other hand, if your system requires a very powerful microprocessor, okay, it is not recommended to use micro C lah, because micro C, the size is small. So it means that the chip or the micro P that they use is not very high performance compared to a micro P based product. Right. So this is some of the micro C flavors lah, right? So for example, you have from Motorola 68HC05 until 68HC12. And you can also have micro C from Intel's, the S5000 and so on. From Atmel, you also have Atmega or ARM-based, which is from Arduino Due. Alright, you can also get the micro C from Arizona Microchip Technology, which is the PIC series. And you can also get from Hitachi's, and you can also get for Samsung and so on lah. So we have lots of example of the micro C that has been used throughout the world or throughout the university. Okay, right. So in addition to that, you can also design your own development board, right? So development board, it is actually depending on your applications, all right? So this is the CPU, which is your microprocessors. And if you want your system to have some buttons function, so you can have your button here, all right? If you wanted to have some LEDs, you can put LEDs here for status and so on, right? So this is the example of Atmega 4888168. So this is a customizable microchip development board, right? And also this is a tiny 8-bit development board. So as you can see here, they have the relay here. Okay, so you can customize your own development board based on the system that you use. So as you can see from both application, right, they are using, we call it a PCB board to design the development board. Because PCB board, it is actually easier for you to design, easier for you to execute, and it is less prone to, we call it circuit failure, right? Because you didn't use, any wire like inside the donut board and so on. Right, so this is the DIY, do-it-yourself development board example. Right, so this is the COTS board-based hardware. So COTS is actually component of the shelf. Oh, I'm sorry, COTS is actually commercial of the shelf. So commercial of the shelf is actually hardware products that are ready-made and available for sale for the general public, right? So it means that it is already there. What you have to do is just buy it and just using it, right? So COTS board is actually option for microprocessor and microcontroller hardware board for use in embedded system. Okay, so you have two options if you wanted to use macro P or macro C. The first option is to design your own board, or the second option is just to use the COTS board lah available, right? So for example, for COTS board, okay, as you can see here, Rabbit 2000. So it is actually 8-bit microcontroller, okay? And then Arduino Duo here. So Arduino Duo here is actually 30-bit COTS hardware lah, which is the hardware which is widely available. What you can just do is buy it, alright, and you can use it. Okay, so this is the COTS hardware, right? So apart from this, you can also have from Freescale, 68HC11, PIC, DSP-IC 32, Intel, and also this is the Zilog one lah. Okay, Zilog Rabbit 2000. Alright, so this is the example of COTS hardware. Okay, commercial off the shelf. Okay, which is readily equipment or readily macro C, which you can just use it. Okay, in your embedded system applications. Right, so this is more advanced. Okay, advanced versions of COTS. Okay. So inadequate use of microcontroller, so high-end embedded processor, okay. So ARM-based processor, for example, the Raspberry Pi here, they use ARM-based processor, okay. Decreased power consumption and space, additional input-output COM port and ROM all on the single chip. Use of Linux, okay, for Raspberry Pi, you can also have Raspbian OS, and you can also install Ubuntu here, okay. So it is Linux-based systems. MS-DOS, Embedded Windows, SOS, vast library support, save money and shorten development time, window based on Linux-based and Linux-based embedded products. So this is the example of this more powerful COTS hardware lah. So as you can see here, you have Raspberry Pi 5 here, okay, 64-bit, and also NVIDIA Jetson Nano here, which is also 64-bit, right? So the upgraded the version or the latest the version, it means that the higher performance the system is, right? Okay, so next is embedded system prototyping. So if you wanted to, we call it design a prototype, a system prototype, so you need to also use embedded system, which is being enhanced for prototyping lah. Okay, which is small, low volume embedded system. So if this is just for an example lah, PC104, use DOS, Linux, NetBSD, MRTOS, or low power. So this is the example of via EPIA. So it is actually high power comparable to PC. Okay, and also in terms of ASIC and FPGA. Okay, FPGA, if you want your system to have some flexibility, you are required or you are recommended to use FPGA. But if your system requires a very high productions, okay, you want to produce in high volume, you are recommended to use ASICs. Okay, so next is the ARM versus PIC versus ABR. It is actually just like the we call it comparison between the microprocessor. Okay, every microprocessor has their own advantage and disadvantage. Alright, so next is the embedded system peripherals. Okay, peripherals is actually the things that you are connected to your embedded systems. Alright, so in terms of communications, so you can have several communication interface lah. Alright, so for example, serial communication interface, RS232 or RS485, right? And then you can also have synchronous or asynchronous serial communication, for example, I2C or SPI. And then you can also connect it via USB. Okay, you can also connect it via MMC, for example, your SD cards. Okay, sometimes your embedded system also provide you the field buses, CAN buses, LIN buses, or Profibus. Alright, sometimes you can also connect it by using PLL, which is, for example, for the timers. Okay, for the discrete system, for example, inside the Raspberry Pi, you connected your input-output by using the GPIO. Okay, analog ADC, DCA, analog digital converter, digital analog converter, right? And then in terms of debugging or programming, you can also use GTAG, USB, and so on. So there are several modes of peripherals, several modes where you can connect your peripherals to your embedded system. Okay, so this is actually customizable, depends on the embedded system itself. Sometimes embedded system, they just use USB. Sometimes embedded system, they just use GPIO. Okay, so it is actually depending on the embedded system. Right, so how you wanted to choose an embedded system which is suitable for your applications, right? So meeting the task at hand efficiently and cost effectively, okay? If your system doesn't require a very powerful, we call it application, for example, your system just wanted to read the data from the sensors and just wanted to move the motors. So you can just use 8-bit controller, right? Or 8-bit microprocessor. You don't have to go beyond to use 32-bit or 64-bit. Do you know why? Because it is actually overspec. You actually overspecification your system. Okay? It is not good because it will actually cost more, and it is not good if you wanted to commercialize the product, right? So it is actually depending on the speed or real-time execution. So if your system require a very high speed or a real-time execution, so you must choose a micro C, or you must choose the embedded system that supports real-time execution, and also the embedded system that can run something with a high speed. Okay? And the second part is the packaging. If your system required a very, very small application, so you need to use an embedded system which is small in form factors. Okay? And then in terms of power consumption, so basically when you wanted to design a system, you already have the specs of the power. Okay, the power supply that you have. For example, for this system, they only have 5 volts. So what is the embedded system that can support 5 volts supply? So you need to search on that, right? And then the amount of RAM and ROM, the number of I/O pin and timer interface. So in terms of I/O pin, it is also important. If you know your system have how many sensors and how many actuators, okay, you must choose your embedded system or embedded controller which can suit your system. Okay, if for example you have 5 sensors and 5 actuators, okay, you cannot use embedded system which has less than 5 input output, because you cannot connect for example 1 or 2 sensors because you don't have enough input output on your embedded system. Okay, so you must be clear on your I/O of your system, okay, before you buy your micro C, before you buy your embedded system. Right, so easy to upgrade to higher performance or lower power consumptions, and the cost per unit. So if the cost is your concern, so you need to choose a cheaper or a more expensive lah. So it is depending on your cost of your embedded system, right? And then when you wanted to choose an embedded system, how easy to develop the product around it is also a consideration. Okay, for example, if you are already familiar with the use of C, maybe you just can use the Arduino. Alright, if for example you are actually very powerful or very expert in Python, maybe you can consider by using Raspberry Pi. Alright, so how easy to develop the product around your embedded system is really important, because it can reduce the development time of your embedded system. Right? So if you wanted to reduce more development time, you must choose the embedded system that can execute or that can develop a system which was more familiar to you, right? Okay, the last one is the ready availability in needed quantity both now and future. So if you wanted to design a system and you wanted to commercialize it later on, you must know you must also survey an embedded system which is actually ready, always available now and also in the future. Because in the future, when you wanted to commercialize it, you need to have the same embedded system, right? So that you can or you can just you can just market it by using the same system. Okay, if for example you use Raspberry Pi 2, okay, right now Raspberry Pi 2 is not sold anymore, right? So it is hard for you to duplicate the same system with by using the same embedded system, right? So for that situation, you need to choose another controller. When you use another controller, you need to develop again, right? So it is important for you to know the ready availability in needed quantity for both now and also the future, right? So design challenge, optimizing design metrics. Okay, so the common metrics that we use to optimize our design, okay, the first one is the unit cost. So unit cost is defined as the monetary cost of manufacturing each copy of the system. right? So for unit cost is the cost per unit. For example, you wanted to design one system which is to detect the presence of the person inside a room. Okay, so for this you use Raspberry Pi, right? So for this application of using Raspberry Pi, you need to we call it calculate the total cost, okay, for 1 unit of person detection inside the room. Okay, that is the unit cost. All right. Next is the NRE cost. So NRE cost is the non-recurring and engineering cost, which is the one-time monetary cost of designing the system. All right. So we took the same example. Okay, the unit cost, the example of designing an embedded system to detect the people inside a room. Okay, so the unit cost is the cost per unit. You have your Raspberry Pi, you have your camera, and you have your algorithm inside your Raspberry Pi. So what is the unit cost? Is the cost for you to manufacture 1 unit of the people detection system. Okay, but for NRE cost, it is actually one-time cost only, okay, of designing the system. Okay, for example, you haven't developed the people detection system yet. Okay, right now you buy this Raspberry Pi, you buy the, we call it you buy the camera. Okay, and then the cost of the programmer, if you are hiring a programmer, the cost of the programmer to develop a people detecting system. Okay, so when you finish develop one system, that is the NRE cost. Okay, so when you develop a system, you package it and then you market it. All right, you market your product. Okay, so each unit, how much it costs is the unit cost. Okay, NRE cost is the cost for you to develop the system lah, right? So next is the size. The size is the physical space required by the system. So the size is just the normal one lah. Okay, what is the size of the system? How you want to define the size of the system? So that is the matrix of your design matrix of your design challenge. Okay, the performance. So what is the execution time? Is the system is operating in real time or not? Right? And then next is the power. So what is the amount of power required, okay, for your system? If you use battery, how long the battery will last, and so on, right? And last one is the flexibility. So flexibility is the ability to change the functionality of the system without incurring heavy NRE costs. Okay, for example, the people detection system, right? If you wanted to change into object detection system, right? How much does it cost? Okay, how flexible is it? Is it we can just simply change into object detection system, or we can simply change it into a color detection system? So that is the flexibility of your design. Okay, so if your system requires a very high flexibility, you must get ready with some of the modification of the system, right? Okay, so this is all of the common metrics lah. Okay, and then we also have additional metrics in the next slide, right? The first one is the unit cost per unit, all right? NRE cost to develop, size of the system, the performance of the system, the power required for the system to run, the flexibility of the system, how flexible the system is, right? And the next common metric is the time to prototype. Okay, so the previous one is NRE, is the cost of the development. This is time to prototype. Time to prototype is actually time that is required starting from when you wanted to design the system until you finish a working prototype of the system, right? So that is time to prototype. So if you wanted to reduce time to prototype, you must use an embedded system which is very familiar to you. Okay, and then next is time to market. The time to market is actually the time required to develop a system to the point that it can be released and sold to customers. Okay, so time to prototype is just to make it function. Okay, after the system is being function well, right, you need to package the system. Okay, after you package the system, all right, it is time to market, right? So when the system has been packaged in a very neat compartment and so on, and then you are ready to market. So that is the time to market lah, the time required for you to release the system to the customers. All right, and then the next one is the maintainability. So how maintainability, the ability to modify the system after its initial release. Okay, for example, is there any patch? Okay, is there any modifications that you should do in order for you to improve the maintainability of your product? Right? So for example, for your mobile phone, the maintainability is the software update. Okay, after its initial release, for example, iOS 16, you are using it. But right now, they already have iOS 17. So that is the maintainability. How you will be able to modify the system after you already release it to the customers. Okay? Right. The other common metric is the correctness, safety, and so on. Right? So there are some designing metrics that are really important for you. Okay? If you wanted to design a system which is very robust, you must make sure that the system has good maintainability, good price, good size. So there are lots of elements that need to be considered in designing an embedded system. Alright? So you can just refer to the common metrics that are usually used, okay? And you can use these metrics before you designing your system. Alright? So my tips is just if you have a problem, okay, and you have the idea to solve the problem, and then you need to choose your embedded system. Okay? My tips is just, you know your skills, right? You are good in Python, or you are good in C, or you are good in other programming. So you choose the embedded system which is more familiar to what you expert on. Right? First, you wanted to reduce the time to prototype. Okay? So if you reduce the time to prototype, you can reduce a lot of costs, right? And then from there, you can consider lah, if you have some constraint in the cost, you can consider the unit cost and RE cost. If your system require a very small application, you need to also consider the smaller size of your embedded system, right? But if your system doesn't require a very high performance of embedded system, maybe you can just consider 8-bit or 16-bit of your macro C. Okay? And then in terms of power, if your motor requires a lot of power, if your we call it system is being installed in remote areas where the power is quite limited, so you need to use a macro C or an embedded system which is low in power consumptions, right? Okay, so that is all for our class today. So the class today is just the introductions of embedded system. What is the example of the embedded system that we can use in our applications? Okay, what are the types of embedded system? 8-bit, 16-bit, 32-bit, 64-bit, and so on. What is the differences between microprocessors and also microcontrollers, right? And what is the design criteria that you need to consider when you are designing an embedded system? So that is all that we have learned in chapter 1. Right? So in the next chapter, we will learn in detail how you wanted to program your embedded system, how you wanted to use your embedded system, and so on. Right, guys? So I think that is all for our class today. Okay, so we will meet again next week physically. Right? So thank you very much. Assalamualaikum and have a good day, everyone.